Right. In chemistry, oftentimes to make reactions happen, especially among ionic compounds, they must be dissolved in water. And while that's not the only kind of solution, that is the main one we'll be working with. So if you remember back at the beginning of the year, we did some classification of matter. Okay, a lot of it had to do with how you were able to separate things. There was also descriptions of, uniformity, things like that. But just as a reminder, solutions fall down at the bottom here as part of a homogeneous mixture. Okay, so they can be separated by physical means, and they're mixed together to the point where they are evenly spread throughout. Right? It's not easy to see, the layer of salt and the layer of water. Salt water looks the same throughout. Okay? So just a couple of vocab terms. A solution is always made out of a solute and a solvent. Solute is the thing being dissolved, like salt or sugar, or even carbon dioxide in soda pop. Whereas the solvent is what's doing the dissolving. Most of the time that's going to be water. Okay? But there are times when, say, an oil would be a better solvent than water. So when it comes down to solvents, okay, like will dissolve like. So there's two major kind of groups of solvents. There's non-polar solutes and non-polar solvents, which really just means there's no charge. Okay? And there's going to be no attraction to any things that are charged when you're dealing with a non-polar solute and solvent. Okay, all of these examples, you don't need to know them specifically, but I would know that they're, oils, carbon compounds, things like that. Fats. Whereas polar and ionic solutes are going to dissolve best in polar solvents, water being the main one. Okay, and what's going on here is that everything has some sort of charge, so you can get attraction. Specifically, water being a polar molecule, it means that the oxygen end of the water tends to hold on to the electrons more often than the hydrogen end, which makes the oxygen end slightly negative and the hydrogen end slightly positive. So if you put an ionic compound inside, what will end up happening is the slightly negative end of the water is going to attract the positive ion and separate it from the negative ion. And opposite of that, the slightly positive hydrogen end of water is going to attract and separate the negative ion. Okay. So something that comes in handy with solutions are ionic and net ionic equations. So a lab that we've done before, which involves solutions, was our reaction of sodium carbonate and calcium chloride. So the first thing if you're asked for an ionic or a net ionic equation, you still need to write out the normal equation first to get your balancing done. So sodium carbonate is Na2CO3 plus calcium chloride, which is +2 - 1, so calcium and 2 chlorines. And those are aqueous, because those are dissolved in water to start. And then in a double replacement reaction, you can think of that as either the two negative pieces switch or the two positive pieces switch. You can't switch one of each, because the only way compounds will form afterwards is by one positive, one negative. Okay, so if we switch our sodium and our calcium, it's going to become calcium carbonate and salt. Okay, to balance it, I have to throw a 2 in here. And then to add my states, the calcium carbonate was the solid, and the sodium chloride stayed aqueous. So, ionic equations, which are generally the first step towards getting you to a net ionic equation, all you do is rewrite everything that's aqueous as their ions, because in water they're not actually going to be stuck to each other. They're going to be separated into their ions. So we've got Na plus, and this is why you want to write your balanced equation first, because all of the numbers the subscripts and the coefficients actually get written as coefficients on the ions. Okay, so we're going to have 2 Na plus CO3 2 minus plus calcium 2 plus chlorine minus, and 2 of those. And again, going to throw my states in here. Okay. The net ionic reactions are usually a little longer to write because you have to separate everything out and actually put the ions in there. So, on the other side, you don't need to split up the calcium carbonate because that is a solid. It forms a precipitate. It comes out of the solution. Okay? So it's not broken up by the water anymore. So that stays written as calcium carbonate. But then the sodium chloride, which is still aqueous, has to be written as 2 Na plus and 2 Cl minus. And I'm going to go put my states in here. Solid, aqueous, aqueous. All right. Now, a net ionic equation focuses in on the non-aqueous product. All right. And really just shows what's necessary in this equation to make the calcium chloride, which ions are required. Another thing is we cross out spectator ions, which are there because they were attached to the necessary ions, but not actually part of the equation. Okay, you can spot a spectator ion when they are in an ionic form in the same number on both the reactant and the product side. So that means sodium, 2 Na plus, looks the same on reactant and product, is one spectator ion, and then the 2 Cl minus is the other one. All right. The net ions, or the ions that are actually required for this reaction to take place and make the solid calcium carbonate, are the CO3 2 minus and the Ca2 plus. So your net ionic reaction would look like this. CO3 2 minus aqueous plus Ca2 plus yields, and that should be aqueous, CaCO3 solid. Okay. So with these, it is important that you always write out your states, okay, because that's one indicator that you're doing everything right. Okay. And then one last thing you'll need to know about is solubility rules. All right. For solution reactions, all right, it is useful to know and be able to expect if something should form a precipitate or if it should stay dissolved in water. So just some general rules that work for predicting this, and we'll use that to look at the list of things I have written off to the side. But this chart is something you have in class. Keep it with you. I'll give it to you on tests. So the left column tells us compounds, okay, types of ionic compounds. And then the right column gives us exceptions to the rule. Okay, so the first chunk, we have things that will always be soluble. I mean, they're always going to dissolve when you throw them in water. Okay? So one thing without any exceptions is stuff from group 1A, so anything that has a +1 charge, and ammonium, which also has a +1 charge, those will always dissolve, regardless of what the negative half of the compound is. Okay? And then the next three are polyatomic ions, nitrates, perchlorates, and acetates that have no exceptions, regardless of what's attached on the positive side, will always dissolve. Okay? Now the last two groups, chlorides, bromides, and iodides, again, regardless of what it's attached to, will always dissolve unless it is this short list. Okay? So if you have silver bromide, that would form a solid. It wouldn't dissolve. If you have lead iodide, that would form a solid. It wouldn't dissolve. Okay? And then sulfates, again, most of them will always dissolve when you add them in water, unless the positive end happens to be on this short list. Like mercury sulfate would form a precipitate if that's something you made, or wouldn't dissolve. Or barium sulfate. Okay? Now, the second half of this list, the insoluble compounds, the rules change. These will always form a precipitate, or cannot dissolve in water. Okay? So carbonates always form solids unless it's attached to something from group 1 or ammonium. Okay, which is why in the reaction we were dealing with, when we started with sodium carbonate, which sodium is in group 1A, we were able to dissolve it. All right? But then when it became calcium carbonate, which is in group 2, it precipitated out and became a solid. Okay? Phosphates follow the same rule. Phosphates will always form solids unless they are attached to something from group 1A. All right? Or ammonium. And then hydroxides follow pretty much the same rule, will always form solids unless attached to group 1A, ammonium, and then there's two other 2+ charges that will affect them. All right? So, looking at the list off to the right, see if you can use the chart to say if it would be a solid or if it would dissolve. Okay? So, KNO3. Based on that, there's 2 reasons why you would say that that should dissolve. It falls into group 1A, K does, and nitrate is on the list, and there's no exceptions for either of those. Okay, so why is that working? Okay, the CH3OOH, or acetic acid, okay, it has acetate and then it's attached to hydrogen. So again, 2 reasons. Acetate always dissolves, and hydrogen falls into group 1A, so that's always going to dissolve. Okay, silver chloride. So if we look at our list, I find chlorides, those always dissolve, except for the fact that silver is one of those exceptions. So that would be a solid. Okay. Lead carbonate. So I find carbonate. Carbonate is always a solid unless attached to 1A and or ammonium. Lead doesn't fall into that group, so this is going to be a solid. Okay. And then ammonium phosphate. A couple different places you could look. Anything that's attached to ammonium is soluble. You can also confirm that when you look at phosphates, the exception to phosphate always being a solid, ammonium falls into that group. So that would dissolve. And then barium hydroxide. Okay, barium's not on a list, but hydroxide is. And hydroxide will always be a solid unless attached to group 1A, ammonium, strontium, or barium. So this would dissolve. So that's how you use the chart.